Hello and welcome back. So now let's build a very simple 1D FEM solver for our test case. So I'll be doing this live on MATLAB, but really the idea is to understand the pseudocode. I'll also be providing scripts in Python and Julia, which would do the same thing. But really the idea is to understand the logic and the nuts and bolts behind finite elements. So as I would be writing down the code, I will also be explaining the meaning of each line, and so you could easily port this to any language, C, C++, or any language that you are really interested in. So let's first define a small workflow which can tell us the sequence of how to start building this from scratch. So the first part would be defining your test case and parameters. So these are the parameters, the constant parameters which are defining your model. Then we would define the mesh and connectivity. So the connectivity is really important. So we have to build a connectivity list. Then we have to do the pre-computations at Gauss points. Then isoparametric mapping. And isoparametric mapping will really allow us to build the physical derivatives, and then we can actually do the element by element integration and local matrix assembly, and finally we'll do the global assembly and solve, followed by post processing. Right, so this is our workflow. So now let's do this step by step. So the first part is defining your test case and parameters. So really there are just three parameters here to define the problem. So there is an inner radius, there is an outer radius, and there is the directlet condition at the inner boundary. So let's start off by writing them down. So our inner is equal to 1, our outer is equal to 12, and phi inner is equal to 50, right? So these are our three parameters. So now let's go to the mesh. So in the mesh we have we first have to so let's just define the mesh through the number of elements. So let's start off with 100 elements, and let's take linear elements. So let's define the radius by using equispaced nodes. So for this we use the linspace function, which will just run from our inner to our outer, right? And the number of nodes will be n-lm plus 1, because because we are using linear elements, so they will be n-lm plus 1. If we used quadratic elements, these would be 2 into n-lm plus 1. Okay, so let's stick to linear elements and let's move ahead. So now let's build the element node connectivity. This is really important. So in case of unstructured grids, this is a bit harder and needs more bookkeeping, but in this case this is very easy. So I'll just build this list here. So I've initialized it as a parameter lm. So here you have the number of rows which are equal to the number of elements. So each row corresponds to one element, and then there are two columns inside it. So for element 1 you will have two nodes, 1 and 2. For element 2 you will have again two nodes, 2 and 3, and so on. Okay, so very simple, and we can just use a for loop for filling this. And simply we'll have something like this, because in the first element starts with 1, the second element starts with 2, the third element starts with 3, and so on. So I0 is just my first node, and the second node is just I0 plus 1. So I could just write this I0 plus 1. So very simple connectivity list. If I want to go for quadratics, I would just do this, right? I would just have 3 nodes, right? So I would just add one more node here, and yeah, this has to change. This would become something like this. Yeah. So in this case we are just looking at linear, so we'll just restrict ourselves. Okay, so this is the element to node connectivity list. So whenever I call lm of e, all the rows, so I can just if I call lm of 4, so then I'll just go to the 4th element and I'll just grab those nodes, right? So you can understand this is very useful in unstructured meshes, right? So you can just grab the nodes from any element even if they are scrambled. So it is really important in those cases. Here it is quite trivial. So now let's go to the next step, which is pre-computation. So I have just saved these Gauss points here. So I have derived in the previous course, I have just derived the 2-point Gauss rule. If you are just interested in it, you could go through it just to understand the basics. But really these values are just available on the internet. And so we are using shape functions and Gauss points defined from 0 to 1. So the master element is 0 to 1. So when you use 0 to 1, your shape functions as well as your Gauss points will have certain values, and in another master element both of them will change. So you just have to make sure that both of them are compatible. And so these are our Gauss points and these are our shape functions. So if I want to pre-compute the shape function at a Gauss point, I will just say shape lin of Gauss point of g, I mean Gauss point of 1 or Gauss point of 2, and I'll get these values at those Gauss points. Okay, but now this is not enough, because if I expand this, right, I have these kind of terms, d psi by dr, right? So psi is just equivalent to n here, right? So but here we have dn by d psi, and psi is your master element coordinate and r is your physical coordinate. Okay, so we have to do that transformation, and for this we need the isoparametric mapping. So let's just do that. So for that we need a parameter which is like the j-like term, which we discussed in the revision. So this is just your dr by d psi, right? So you could think of, so if you are so let's say our element are the radial values at the elemental nodes. Okay, so for the isoparametric mapping, I can just do r element into dn d psi. Okay, and similarly I can also define r iso is equal to r element. So this is too long, let me just write it as re, right? So re multiplied by n. Okay, so this will give me the radius value, the physical radius value, which is interpolated, right? So so these are my pre-computed these and these n and dn dxi are basically my pre-computed shapes at a certain Gauss point, right? So this should also be a function which I can call and do the isoparametric mapping. So let's also define the third one, which we the third output that we need, and that is L, which is basically your scaling. So that is simply dr by d psi. So this is, so r is your physical element, psi r refers to your physical element, and psi refers to your master element, rather the coordinates, right? And so you can understand that the ratio is basically like a scaling factor, right? So when you want to do an integration on the master element, you can just multiply that integrand by L. Okay, so we have already seen this in the revision and in the previous course as well. So it's pretty straightforward, and let's just define this as a function so that we can call it. And these are our outputs really, r iso comma dr dxi, right, and L. So these are my outputs, and let me define a function called as isomap, and these are the inputs, right. So this is my function, and so both of these are basically, you could think of them as helper functions. So let's just push them a bit down. And now that we can use these helper functions to actually construct our physical derivatives, right? So let's just do that. Let's start building our global assembly and element and local assembly. So for that, first we also have to initialize some variables. So let's start off by counting the number of nodes first, and then let's initialize the global stiffness matrix and the global force vector, right? So let's say the total number of nodes is equal to the length of r, right, the r vector. And then let's define your global stiffness matrix. Let's initialize it. So this is basically if your number of elements are 100, so number of nodes are 101. So stiffness matrix will be 101 by 101 because you are writing the bilinear form there, and the force vector is just the linear form, so that will be 101 comma 1. So 101 rows and 1 column. So we have initialized the global variables. So now let's start off with the assembly. So let's run a for loop over all the elements, right? And for this, let us also define the nodes and the local matrices. So we'll have to initialize local variables now. We have already initialized the global variables. So now here the connectivity list will help us, right? Because I can just say nodes is equal to lm. So the number of element which I am in, and I can just pull in the node values, and then I can just say re is equal to r at those nodes. Very simple, right? Becomes very easy because you have your connectivity list. And now let us initialize our local stiffness matrix. So this is just 2 by 2, right? Zeros of 2 by 2 because we are using linears. If we were using quadratics, we would just go to 3 by 3. All right. So now we can actually start doing the integration. So let's define the Gauss points. So we have a 2-point rule. So now let's pull in these guys. So these will really help us. So we want to start defining the derivatives. So this psi we will just replace with the Gauss point at G. Okay, so the two Gauss points. And so now let us also define our actual derivative. So I'll call it as dn. So this is the physical derivative, and I can just do it by dn by dxi upon dr by dxi. So this is my derivative, and so now I can start writing down this actual equation, right, this form. And so you could write this as two for loops, for test node, for trial node, and you could just do ke of test node, trial node, right? And then you could just do the dn of test node into dn of trial node, right? And then you would get this 2 by 2 matrix, right? So this 2 by 2 matrix, of course you have to multiply by r as well. So so you will have to multiply by r iso raised to 2. We'll have to multiply by L the scaling factor and also by Gauss weight, or yeah, the Gauss weight, G weight of G. Okay, but this is a bit more elaborate. An easier way to do this is to just look at this as an outer product, or just multiply the test function by the transpose of the same test or trial function. So they are really the same in Galerkin's method. So you just take the same vector and just multiply it by its transpose. So you just do dn by dn transpose, right? So this is a much more easier way of doing it, so you don't need for loops. And so dn has two values. It is a vector of two values, and when you do this multiplication, you get 2 by 2. Okay, so this is your ke, and let's remove this test node, trial node. So don't need any for loops. This is much more easy. All right, so I have made a mistake here. I need to, yeah, so because I have two Gauss points, so I have to add them. Okay, and so before completing this second loop, I have to assemble this into the global structure. Plus ke. Okay, so this will just plug in these blocks into the global structure, and since we are doing this addition, so at the common nodes you will also, these ke blocks will just add to each other. Okay, so we have our global structure now. So now we just have to impose the Dirichlet boundary condition and the Robin boundary condition. So that part is very easy. So the first Dirichlet condition is, of course, the first node. The first node is just at the inner boundary. So we just zero out the row first, and then we put the diagonal element equal to 1, so that it exactly multiplies with the value of phi, the unknown phi, at exactly this point, right? The diagonal element, and we set the RHS equal to 50, right? Your phi inner value, this one. So this is the imposition of Dirichlet boundary condition. For Robin boundary condition, we already discussed. So we just use the last element of the last row. We just have to add psi into r outer, right, square into your phi by r, right? So phi is your unknown, and this is your stiffness matrix. So anyways, you will be multiplying by an unknown, so we'll just ignore this. So this is this factor, r into d phi by dr is basically phi upon r. So here r is basically the large r is basically your 12. So you are just having r outer multiplied by phi. So that is in the unknowns vector, so we can ignore it, and it is multiplied by psi. But I am not showing psi here because it is just there is just one node here at the end, and you are multiplying by a test function. So there is just one test function here, and because this is just a point integral here. So if you had a face or a line, you might have multiple elements here, but here there is just one element, and that element is just one exactly at that boundary point. So it's just like you are just multiplying by 1, right? So eventually it just boils down to r outer plus 1. Right, so this is your Robin boundary condition. So now we have imposed the boundary condition, so now we can also solve. So let's solve this by k\f. So this will give us our finite element solution, and let's also plot it against the finite rather the analytical solution, and the analytical solution will be 50 upon your radius, right? So this is your analytical solution. So if we have done everything correctly, this should just work. So let's plot r comma FEM, right? Hold on, plot r comma phi a, right? So all right, so let's just run this. Right, so this is our solution, right? And you can see that it fits really well. Let me do this once again, right? So this is our solution, and you can see that the red part is the analytical solution. These blue dots are your FEM solution, and you can see that it matches really well. You could also calculate an error norm. So error is equal to norm of phi a minus phi FEM, right? Take an absolute value of that. Right, so there is some issue here. So yeah, so phi a and phi FEM are just flipped, so just can just take the transpose, right? So this is your error, and so I have not really gone into detail and calculated the L2 and L1 error norm. For that, you actually have to do a proper integration using Gauss points. So I have shown that in the previous course as well. Towards the end, I have given a code for actually doing this, and we'll also look at the method of manufactured solutions and error analysis as we go ahead. But right now, just let's crank up the, let's do some edge refinement. So let's run this. So this is your error when you have 10 elements. So when you have 100 elements, you can see the error goes down, right? So this is your edge refinement. So now let's also try, let's see if we can do the polynomial refinement. So so here are your quadratic shape functions. So let's just paste them here. So yeah, and we'll keep the same Gauss rule because we can use it up to cubics. So let's just keep the same Gauss rule, and so this will become 3, this guy becomes 2. Let's add one more I0 plus 2, and this will become 3 by 3, I guess, and this should become 2 star LM plus 1. I think that's all. Yeah. Right, so now you can see that the error is much less. So let's try to compare this with right? So you can see that the error is much less. So we had a value, I think, which was 3 or something. In the case of linears, it was more than 1 basically. And here you are having a much, and you could also see that those points were off the grid, and now you are getting a better solution because this is p refinement basically. So this is our working MATLAB code, a code which we just created live, and you could write this down as well, or I will provide this file in a downloadable format. I can also provide these files which are in Julia, so I'll just run this on VS Code. So this is a Julia implementation. So exactly the same thing, and there's also, I guess, a Python implementation. So right. So this is your Python implementation, again the same thing. So the code structure is also exactly the same. Okay, so you just have the exact same thing. So this is how we code the finite elements, and you will see that when we go to higher order elements, you have already seen it's very easy to just modify the code. Almost nothing has changed in the basic code structure. We just changed the shape library, right? If we want, we just have to change the Gauss points, which are just here. The Gauss points are Gauss rules. So this you can just run from 1 to num Gauss, right? So it's very simple to crank up the order. It's not so easy in the other methods like finite volumes. Of course, they have other benefits, like they are good at mass conservation, and finite elements is not good at that. If you want the best of both worlds, you will have to go for discontinuous Galerkin, which has a lot of DOFs. So there are always pros and cons. So no method is the best method, but these are the advantages. The advantage of finite elements is, of course, that you can crank up the order very easily, and you will see that this code structure is almost the same, even if we go to 2D or 3D. It's very easy to code. Okay, so that's what we'll do in the next lectures. I thank you for paying attention, and please have a look at the code, have fun with it, play around, try to do some error analysis. So by the time you come for the next course, maybe you will be quite prepared with the entire finite element ecosystem after learning 2D and 3D, and then we'll be able to make a headlong jump into full-blown Navier-Stokes coding. So that's our aim. So firstly, before going there, we have to do the 2D analysis and 3D analysis, and for that we have to make meshes on Gmesh. We have to read that mesh, unstructured meshes. So let's start working on that, and we'll do that in the next talk, in the next lecture. And I thank you for your attention, and I'll see you again.